Possibilities. Have you seen Hitchhiker's Guide to the Galaxy where it's in the war? Yes. There's no difference.
You guys, some of you guys have taken some physics, and I keep bringing it up because even if you don't take a lot of physics, normally for math majors you do have to take some physics. The reason you do that is because so many of the things we talk about in purely mathematical terms make so much more sense when you can imagine how they affect something you can really hold. So a lot of what we're doing right now, and a lot of what happens in chapter 14, makes a lot more sense when you relate it to something physical. For example, a lot of you guys have seen like electric field lines around a charge, and more of you have seen magnetic field lines around a bar or something, bar magnet. Have you guys all seen that? In fact, way back somewhere in your life, you might even have had a piece of paper over a bar and thrown some iron filings on top, and actually traces out the field lines. Depends on what the hell has happened in your life, but sometimes teachers will do that with you in science class or whatever. So what we're talking about today, some of you guys might have been exposed to something called slope. Slope field? So that's another example of a vector field. All a vector field is given, actually let me not get ahead of myself. One way to define a vector field, and we'll use capital F. The most general way to do it, a vector field in general is some function of x and y along the I direction plus some function of x and y in the j direction. So you notice how at every point in the domain of those functions, I've defined a little vector. So ignoring the little shape in the middle, do you see up there at the top the definition of the vector field? Let me start with one that's a little bit less freaky. Let's just start with xy. So this vector field, and they're using the wrong symbol, so that's too bad for them. This vector field example would be xy. So f of xy would be x, g of xy would be y. So at every single point, so for example, at the point 2, 0, what is the vector field at that point? What's the vector output that you get? It's not that bad, because it's really just a vector that points in the same direction as the position vector would, if you think about it. This would just be, so this would equal at 2, 0, it would be 2, 0. Right? It's incredible. So at 2, 0, that's why it points along the axis here, right? What would it be at the point 2, 1? At 2, 1, it's the vector 2, 1. Might have been negative last time. So at 2, 1, you see how it's pointing at 2, 1. It's pointing in the direction of 2, 1. It's pointing parallel to that. So this is a very, very simple definitions, simple functions that I can use to define a vector field. Do you remember this sort of? There are several things that are like this that some of you guys might have done, depending on what your teachers have done with you, what books you guys use. One thing this could represent, do you see how the strength, is it getting bigger or smaller as you go out? Bigger. And what do you think measures the strength here would be, of course, the magnitude. So, for example, at the point 2, 1, what's the magnitude of the vector field? 2, 1. Yeah, it would be the square root of 2 squared plus 1 squared, square root of 5. And at the point 3, negative 3, it would be square root of 18. It's getting larger. And that's why the vector, the little representative vectors are getting larger. Notice if I really wanted to do this, I'd have to have an infinite number of little vectors. So we normally just have representative points. You guys kind of with me here.
2, 1, is that 2I plus 1J? Or is
Exactly. I mean, that's what this here represents, right? You got another way to write this would be 2I plus 1J. That's what that means. This is IJ, and this is just vector notation. Right? So you can either write it in component form or vector notation.
Why do you have a plus in the vector notation now?
Because I had a minus in there for some reason.
Oh, okay.
So I wanted to make it positive.
There you go.
So now watch, if I change the definition, let's see, if I say f equals 1 x plus y. Let's make a few predictions and see if it's true. At the point 0, 0. The vector output would be 1, 0. At the point 3, 1. 1, 4. So it's going to be pointing in that direction from the point 3, 1. Right? So it's going to be a little vector that starts at 3, 1 and points in the direction of 1, 4. Right? What about negative 1, 1? 1, 0. In fact, where's it going to be 1, 0? Along what? It'll be 1, 0 when x plus y equals 0. So the output will be 1, 0 when x plus y is 0, or better, when y equals negative x. So along the y equals negative x line, I should see a bunch of things that are pointing in the direction 1, 0. That's kind of cool. So let me put the picture up there and show you what we just did and see if it's true. Hopefully I remembered this thing they have here correctly. Yes, thank God. So, just to kind of double check, and again, forget about the little loop in the middle. That's actually for a later section. We did 0, 0. Of course, they don't have anything there for a little less. Would be 1, 0, so it's actually pointing along the x-axis. 3, 1 is 1, 4. So 3, 1 should be pointing in the direction 1, 4. So it should have a big slope. You see that? So 3, 1, that makes sense. Should be pointing in the direction of 1, 4. And it is. And we said that all along the y equals negative x line, it should be 1, 0. And if you look, they didn't really, right there, you can't really see it too well, but see that? That's a little vector pointing this way, in the 1, 0 direction. All along the, now I have all along the watchtower in my head. All along the y equals negative x line, it's doing exactly what we predicted. So how are we doing so far? I mean, where do you think this kind of thing is used in other places besides electric field lines and magnetic field lines? Those are basically related. Where else do you think this kind of thing would show up? I don't know if you've ever seen this, if you ever watched the weather. Very often they'll have, I used to live in...
Same here.
I was going to say the weather because, you always see this stuff.
And what's this stuff in relation to? Wind velocity. So at every point in an area, the wind velocity is something, right? And very often I would see, I lived in Virginia and Florida, so we were always big on when a hurricane's coming through, they'd show this little thing that shows as the hurricane went through, they'd have all these little arrows that are like going crazy, and sometimes they grow and shrink, and say, here it is, look, and that's like, yeah, that was about an hour ago, that's why the trees blew over. But you'd see, they show the map of the whole region, and at certain points, they'd have little arrows showing you which direction the wind was blowing. So as the hurricane went by, you could see the arrows turn and then shrink as it goes away. You guys kind of with me? Yes. So anywhere where you have certain properties, different or the same or whatever, over a given region, you can use a vector field. Right? Okay. So, just to give you a couple of... let me see, I don't want to get too far into myself. Oh, here's one form that happens a lot in nature. And somebody tell me, why does, and this is kind of a little physics lesson, when you get further and further away from a light source, right? What happens, of course, to the available light? It's the intensity of the light. It gets less and less. And the beautiful thing, the connection between the math and the physical reality, what's really cool to me, same thing with noise. If you put a speaker somewhere and you get further away from the speaker, of course the sound intensity is going to go down. But is it a linear relationship? No, it's not. Because what's happening, for example, that light, as the light goes out, it's got to cover an area. So as you go r distance away, the light's going to go down by 1 over r squared. Because it's got to cover that intensity, it's got to cover an area of r squared as you move away from it. So it's actually going to get smaller and smaller by a factor of r squared. So a form that happens a lot in physics and nature itself is this here. Blah, blah, blah. And see, right there is what I'm talking about. If P was actually 3, it would be what I was just talking about. Because, to break this up, what do I get if I do this? What is this here? That's a unit vector. I love it. So it's pointing in the direction of the light or the direction of the sound waves and how it's traveling. So this is a unit vector. It's just like the direction of the little arrows, right? Then how long is the arrow is going to be what's left over. What's left over to make this? Let me not put, that's not a dot property. Yeah, it'll be 1 over r to the p minus 1. Cool. So if I do have a cube here, isn't that going to be 3 minus 1 squared? Won't that be the electric field then? And in fact, on an earlier thing I found up here, let me see if I can get there. Where was it? Was it here? Probably not. Too bad for Jeff. I can't remember where it was. Oh, history. Oh, screw you. All right. Anyway. Shoot, I want to show you because they actually had up here an electric field would be related to R over R cubed. So this is on page, let's see, where am I? 964. So what they do at first in this section is they start with 2 dimensions. And then of course we're going to extend everything we're talking about to 3 dimensions. It's not that big of a deal. We've done that before. So right now I've got this. X, Y over R to the P. All right, so I'm in 2 dimensions, so my radius is just, my R is just going to be X, Y. Cool. So a little specific example would be example 2 on page 964. This is going to sound very familiar. We've sort of done vector fields before, a very specific type of vector field. Who remembers how the gradient related to a level curve? Orthogonal, I love it, right? And there was an instance where a contentious picture showed up with ellipse. These are my elliptical contours, my elliptical level curves, and the line that represented the gradients would actually kind of curve as it went through it to keep it perpendicular every time it hit the surface, right? Every time it hit the curve. If I drew all of those, that would be an example of what's called flow curves, which is really just connecting all the little vectors that we get. If I connect them together. So if I get, here's a really nice picture. Go back here. This is in the book too. Come on. There we go, vector fields. So, where'd it go? Here. All right. So of course, if I connect those, I get what's called flow curves. So if I just pop, there. And that's a slightly better visual for how things would move. So if this was wind, so I'm in a tornado or something, and I drop something here, how's it going to move? Like this, right? So those flow curves, it makes sense why they call that. It's how it would flow. I mean, that's sort of like if this is water going down a whirlpool. Because remember, this is like level curves. So maybe this is going down and down like that. Right? If I drop something in, it's gonna, that would actually be more like going in towards the center. But with the way this is drawn, something would just flow this way. Okay, cool. So example 2 is a little more specific. It says, let C be the circle. Squared, right? Yep. Show that at each point of C, the radial vector field, which is this guy, which one is it doing? Oh, just this here. Show that that is orthogonal to the line tangent at the point. Okay, so that sounds a little bit freaky. But how do you show this, a couple things are orthogonal?
Your dot product should be 0.
Yeah, the dot product should be 0. So if I can write the form of the line tangent to this point, to any point, then I can figure out if it's orthogonal to this, to the vector field. So here's how it works. So I'm on this circle. So can somebody help me out? How do I define this for a circle? How to define a circle? X and Y have to be how related to the radius, which is A here. We know this from polar coordinates. What would it be? X would have to be A cosine theta, and Y would have to be
A sine.
A sine theta. Now, how do I get the tangent line?
Taking the partial derivative to find the slope.
Not really a partial on this level here, because we did it before we did partials. All I have to do is take the derivative of R with respect to the parameter. There's only one parameter here, right? So it's not really a partial. So what's R prime going to be?
Negative A sine.
Negative A sine?
And A cosine.
I like it. A cosine. Which is what in terms of X and Y? What is this in terms of X and Y?
Negative Y.
Negative Y. X. Now, obviously that, I don't even have to do work, hopefully. Is that going to be orthogonal to this?
Yep.
Yes. Because negative yx plus yx is 0, right? I can see that.
Would y negative x be orthogonal? Or what?
Say again?
Y, instead of negative yx, would y negative x be orthogonal?
Yes, it would also be orthogonal.
How can you do that without this?
And I could do either one because of the fact that I brought my parameter in. It wasn't defined using a parameter, so the tangent line is officially either direction. So, but what we get just using the way that I defined it is this. Cool. All right, so that's part A. This is definitely orthogonal. And what they're really trying to get at is that connection here. If I draw little, my little vector fields, if I connect them, I should be getting that orthogonal line. It's going to be orthogonal to all the level curves. Okay, so that's the answer. That's the idea there. Part B really is the same idea. We actually did the work already. Part B, I already know the answer. Is that parallel to this, the one that they give me in Part B? Yes, it is this, just unitized, right? Divided by its length, so it's going to be the unit vector in that direction. Okay. Something a little more meaty. What time we got? Oh, good. We got time. Something that we can sink our teeth into a little bit more. Here we go. Cool. So in 3 dimensions, f will now be just some function of x, y, z, g of x, y, z, h of x, y, z. And this is what I was talking about earlier. A specific example of this, a specific way to do this that actually happens a lot, is to create something called a gradient field. And you create that just by setting up the gradient of some given function. So given some function phi, and that's like this is one thing, this is a scalar valued function, it's not a vector valued function. And very often you'll see in high level mathematics they'll use the letter phi for scalar valued functions a lot. So given some function phi, if I take the gradient of it and set that and say that that's my vector field. All right, so obviously I'm going to call this, a really good name for this would be the gradient field. Right? This is a this is a specific type of vector field called the gradient field. Very creative name. We made it from a gradient. Here's the kind of cool thing about this. If any of you have taken any physics, this will sound very familiar. If you haven't taken physics, oh well, I would have said this anyway. This is called the potential function. And of course, this is the gradient field. Okay. So, one example, have you guys ever heard, how many of you guys have never ever heard of kinetic energy and potential energy? How many of you guys have never heard of those things? And you can, it's okay to say never. Sweet. So either you're lying to me or you have heard of it. So the idea is, of course, if I lift this up, I'm providing it with more and more potential energy, because then that gets converted to kinetic as it falls down. So obviously then height is a representation of increased potential energy. You guys with me? So if I climb up and up a cliff and then suddenly it stops and I fall, if I've climbed, the higher I climb, the worse it's going to be for me at the bottom, right? So we've already seen an example of this type of thing. When he drew a topographical map, when they had examples of topographical maps, those were what are called now, what? Those lines that we draw? What was special about those lines? So if I have a little hill right here, level curves. But now, even better, those are locations where if I travel along them, am I going higher or lower? No. I'm staying at the same height. So I'm staying at the same potential. So now we're going to call these not level curves anymore. They are now equipotential. Oh shit. Equipotential curves. And I just want that physical reality, that image of, well, if I walk around a stupid mountain on the same level, of course my potential is the same. I'm not going higher, I'm not going lower. I've got the same potential to die if I fall off this thing, right? So it's equipotential curve. So one example of this whole thing that we've already looked at is a topographical map. So we need the gradient of it. Tell me, the gradient points you in the direction of what? The steepest descent, right? Cool. So that those kind of things carry over. So a lot of what we do in chapter 14 is going to be related to stuff we've already done. All right, let's play, guys. Have a good weekend. Have a good Thanksgiving.
Have a nice Thanksgiving.
Thanks, Brian. first. They'll probably be rest of the year.
It's for the nurturing anyway, but just in case.
Yeah. The problem.
I got to class in my 5th period, I think it's like Friday before that weekend. Sorry.
Yes.
Yeah.
You just have to remind me and get closer so I can have it made ready.
Okay.
Because I probably was going to make it over that weekend.
Oh, really?
But it's fine, I mean, if I make it a little earlier, that makes my weekend a little bit less burden, so hey.
Okay.
Just remind me maybe that, that week, remind me that Monday, so I can start looking at it, so you can make an appointment to get it that Friday.
Okay.
Because I'm bad feeling when it's booked up that last week before finals.
Alright.
Yeah. No problem.
I can't hear